Okay, picture this. You've got a content creator uploading a massive 4 gigabyte 4K video to your platform. They're stuck on hotel Wi-Fi and the upload is taking an entire hour. And then at exactly 99%, the Wi-Fi blips, just for 2 seconds. The connection drops, your server returns an error, and bam! They have to start that entire 1-hour upload completely from scratch. You can bet they are absolutely furious.
So why did this happen? Well, it's because you used a standard S3 put operation for a massive file. When you upload a file this way, it sends the data as a single continuous stream. So if that network connection drops for even a fraction of a second, that stream is severed. S3 just discards whatever incomplete data it received, the upload fails entirely, and basically, you've engineered a system that was destined to fail. But don't worry, let me show you how to actually engineer resilient storage pipelines.
Okay, let's dive into this. Section 1. The solution, S3 Multipart Uploads.
Instead of relying on one fragile stream, this architectural fix breaks your large file into dozens, hundreds, or even thousands of smaller chunks and uploads them completely independently. Now, AWS highly recommends using multi-part uploads for literally anything over 100 megabytes. But hear me clearly on this. It is a strict, undeniable, hard requirement for any file larger than 5 gigabytes. You literally cannot upload a 6 gigabyte file with a standard put operation. S3 will just outright reject it.
And this brilliantly illustrates the difference. Think of it kind of like moving to a new city. A standard put request, that's like packing absolutely everything you own into one massive semi-truck. If that single truck breaks down on the highway, well, absolutely nothing reaches your new house. A multi-part upload, on the other hand, is like packing your belongings into a resilient fleet of 100 small delivery vans. If one van gets a flat tire, no big deal. The other 99 vans still arrive right on time, and you just send a replacement van for the one that failed.
All right, moving on to Section 2, Under the Hood, the architecture. Let's look at the exact mechanics happening behind the scenes here. So how do we actually build this fleet of vans? Well, behind the scenes at the API level, it's a very precise 3-step process. Step 1, your application code makes a request to S3 to initiate the upload. S3 responds by handing you a unique upload ID. Step 2, you split the file. Your code breaks that massive video into smaller chunks, usually somewhere between 5 megabytes and a few dozen megabytes, and pushes them to S3 in parallel. Every single time you upload a chunk, you include that unique upload ID and a specific part number, like part 1, part 2, and so on. Finally, step 3 is the assembly. Once every single part has successfully reached AWS, your application sends a complete multi-part upload request. S3 takes all those individual chunks, stitches them together in the exact order of their part numbers, and creates one single, seamless object in your bucket.
Think about that for a second. You aren't just surviving network drops here. You are fundamentally changing the performance profile of your application. Because the parts are uploaded independently, you can upload them in parallel. If you've got a massive bandwidth pipe, you can push 20 parts at the exact same time, which drastically reduces the total upload duration. And hey, if part number 17 fails because of a network blip, you don't restart the whole gigabyte file, you just retry that specific 5 megabyte part number 17. The resiliency is built directly into the architecture.
Okay, let's jump to Section 3, Scaling with Presigned URLs.
Now, we absolutely need to talk about scaling. Imagine routing a massive 4 gigabyte video upload through your small backend EC2 server. You're going to completely crush your compute resources and max out your network cards. It's a disaster waiting to happen. To bypass these backend bottlenecks, you combine multi-part uploads with presigned URLs. Basically, your lightweight backend generates a unique, secure pre-signed URL for every single part of that multi-part upload, and then hands those URLs back to the client's browser. The user's browser then uploads the file chunks directly to S3, completely bypassing your backend compute. Your servers stay fast, and S3 happily absorbs all that heavy network traffic.
And if those users are uploading from all across the world, you can take this a step further by enabling S3 transfer acceleration. What this does is route those individual multi-part chunks through the closest AWS edge location. So instead of fighting through public internet latency, your data rides the highly optimized AWS global backbone directly to your target bucket. It's incredibly fast.
Section 4, the hidden cost trap. Now, what's really interesting about this slide is this is exactly where things get dangerous. This introduces a massive exam trap. And honestly, it's the exact scenario where developers accidentally bankrupt their own companies.
I'm talking about incomplete multi-part uploads. Think about it. What happens if a user starts an upload, pushes 3 gigabytes of chunks directly to S3, and then simply closes their laptop forever? The upload is never completed. S3 holds onto those hidden chunks, endlessly waiting for that complete multi-part upload command. You actually cannot see these chunks in the standard AWS console, but you are absolutely being billed for their storage space. Over months, these abandoned, invisible chunks can cost your company thousands of dollars. You have to protect yourself here. Now, if an upload fails permanently, your code should call the AbortMultipartUpload API to delete the stored chunks. But let's be real. You can never trust client applications to always clean up their messes. So you absolutely must configure an S3 Lifecycle Rule. You create a rule acting as an automated garbage collector, explicitly set to delete expired incomplete multi-part uploads after a certain amount of days, say 7 days. This automatically wipes out those abandoned chunks and protects your AWS bill.
While we're talking about traps, you've got to watch out for the ETag trap. If you're doing file integrity validation, be warned. For a standard upload, the S3 ETag is usually just the MD5 hash of the file. But for a multi-part upload, the ETag is not the MD5 hash of the entire file. Actually, it's a calculated hash of the individual part hashes, and it always ends with a dash and the total number of parts, like -24. You absolutely must account for this in your application code, or your integrity checks will fail every time. Finally, let's remember how this fits into your event-driven architecture. S3 event notifications will not fire when individual parts arrive. S3 waits patiently until the complete multi-part upload API call finishes stitching the entire file together, and then it fires a single S3 object created event. This is the exact trigger you use to wake up an AWS Lambda function to automatically start transcoding that video for your viewers.
All right, let's wrap this up. Section 5, 3 rapid takeaways.
So, the crucial point is this. Number 1, multi-part uploads are a hard, strict requirement for files over 5 gigabytes, and they dramatically improve your upload speed through parallelization. Number 2, you must implement S3 lifecycle policies to automatically delete incomplete multi-part uploads, or you are going to be permanently billed for invisible data. And number 3, combining presigned URLs with multi-part uploads protects your EC2 compute by allowing clients to upload massive files directly to S3. I'll leave you with one final warning. Never, ever assume a mobile network is stable. Always design your pipelines expecting the connection to drop. When you build this, write your client-side code so that it caches the upload ID, allowing it to retry exactly which part numbers drop, rather than forcing your users to start all over again. Build for failure, and you will achieve true resilience. Which kind of makes you wonder, what other silent bottlenecks are currently lurking in your cloud architecture?